let's dive right into this explainer. Okay, today we're going to look past the hype of 3D printing to truly understand the textbook engineering that is absolutely reshaping modern manufacturing as we know it. I mean, for decades, making a prototype meant sending designs off to manufacturing processes that literally just carved away material, eating up weeks or even months of development time. But what we're exploring today is a total paradigm shift. We're going to break down the exact methodologies, the materials, and the machinery that allow engineers to produce wildly complex geometries directly from a digital file, completely bypassing traditional tools and dice. So think of this as a structured factory tour. Our agenda is simple. We'll start with the layered revolution, move on to extruding and curing, explore the power of powder, check out some really cool real-world case studies, and wrap up with the future frontier. All right, Section 1, the layered revolution. To kick things off, I've got a question for you. What do a highly detailed anatomical model of a human head, a plastic squirt gun, and a high-tech running shoe all have in common? I know, it sounds like the setup to a joke, right? But the answer is actually pretty amazing. All of these were made without traditional tools, without expensive injection molds, and without the wasteful machining processes we've relied on for the last century. And that brings us to our core definition: additive manufacturing. Basically, it's the process of producing a solid, physical model directly from a 3D CAD drawing by building the part layer by layer. See, traditional manufacturing is primarily subtractive. You start with a big block of metal or plastic and you carve away what you don't need. Additive manufacturing completely flips the script. You only put material exactly where it's needed. To really picture this, think about a loaf of bread. If you wanted to create a complex loaf, instead of baking the whole thing and then trying to carve out intricate hollow spaces inside it, you simply build the loaf by stacking up individual paper-thin slices one by one. The computer analyzes your 3D part, digitally slices it into thousands of horizontal cross-sections, and then the machine perfectly stacks those physical slices. Moving right along to Section 2, extruding and curing. Let's look at how we actually make these layers. Our first process is fused deposition modeling, or FDM. You've probably seen FDM around in makerspaces. It's effectively a super precise, robot-controlled hot glue gun. First, a solid plastic filament is heated up and pushed through a moving nozzle that draws out a single slice of our object. Once that layer is done, the build table drops down just a fraction of a millimeter, and the next layer is superimposed right on top, bonding to the hot plastic just below it. But listen, FDM isn't just for basic plastics anymore. Enter continuous fiber fabrication. Machines can now use a second nozzle to lay down a continuous strand of carbon fiber, fiberglass, or Kevlar directly inside a nylon-printed part. We can digitally plan the structural reinforcement, which gives us lightweight additive parts, like motorcycle brake levers, with absolutely incredible metal-like strength. Okay, but what if melting solid plastic isn't your thing? Let's talk liquids. Stereolithography, or SLA, is brilliant because it uses light to create solid objects. You start with a vat filled with a liquid photopolymer, basically a special resin that reacts to light. An ultraviolet laser is focused onto the surface, tracing out a shape. The exact moment that UV light hits the liquid, it instantly cures and hardens into a solid layer. Then the platform lowers slightly, fresh liquid washes over the top, and the laser traces the next slice. Now, taking that liquid concept to the next level, we have the clip breakthrough: continuous liquid interphase production. Instead of lowering a platform step by step and waiting for fresh resin to wash over, clip projects a continuous sequence of UV images from underneath the vat. The secret sauce here is an oxygen-permeable window at the bottom. It works kind of like a contact lens. Oxygen prevents the resin from curing, creating this microscopic liquid dead zone right at the window. Because the part never sticks to the glass, it gets pulled continuously upward out of the liquid puddle. The result? Production rates that are up to 100 times faster than traditional additive methods. It is a real game changer. All right, let's hit Section 3, the power of powder. In selective laser sintering, SLS, we're dealing with microscopic layers of powder. A roller spreads a fine layer across a build chamber, and then a laser fires. But it's not curing a liquid this time, it's literally melting or sintering the powder particles together. And the absolute genius of this method is that because you're building inside a deep bed of powder, all the loose, unfused powder acts as a built-in support structure. When it's done, you pull out a giant block of loose powder, called the cake, and just brush it away to reveal a highly complex part floating securely inside. So here's the crucial takeaway. The process you choose totally dictates your available materials. If you want tough, general-use plastics, you go with FDM solid filaments. Need highly flexible polyurethanes? SLA's liquid photopolymers are your best bet. But if you switch out that laser for a high-energy electron beam and use metal powder in a vacuum, you can literally print aerospace-grade titanium and stainless steel parts that are fully dense and ready for heavy-duty applications. Oh, and powder gives us one more really cool trick: binder jetting. Think of a standard inkjet printer, but instead of printing on paper, it's spraying tiny droplets of liquid glue, a binder, onto layers of powder. This lets us produce stunning, full-color prototypes. For example, you can print a complex medical hand model with perfectly intricate internal details, like veins and bones. It's an invaluable tool for surgical prep. Let's look at how this is actually being used in the field. Section 4, Real-World Case Studies. We can now go straight from a virtual CAD model of a super soaker directly to a physical, working prototype. Back in the day, testing a complex toy like this meant cutting super expensive metal molds just to see if the parts even fit together. Instead, engineers just used FDM to print the individual components out of plastic, they assembled it, and boom, it was a fully functional prototype that actually squirted water. They could instantly verify the design before spending a single dollar on tooling. But we can push this way further than toys. Check out this incredibly intricate lattice structure. This is a material shoe sole designed by Additive. By using that blazing fast clip process we discussed earlier, their engineers were able to test 50 different design iterations in the exact same amount of time it used to take to injection mold just one prototype. They could tweak the thickness of individual struts to tune the mechanical performance perfectly. And that led to the finished FUBTRACTIVE 4D running shoe. Because they aren't constrained by traditional molds, the sole's stiffness can be custom-tuned to an individual athlete's data. You get more support in the heel, more flex in the toe, all printed as a single monolithic part. What's truly revolutionary here is the scale. Adidas proved that this tech isn't just for one-off prototypes anymore. Using Clip, they plan for mass production of 100,000 units a year. Which brings us to our final stop, Section 5, the future frontier. We are moving rapidly beyond just plastics and metals and entering the realm of bioprinting. Researchers are using the exact same additive principles, layer-by-layer deposition, but instead of melted plastic, they're printing with living cells suspended in a liquid carrier called a bioink. The aggressive, long-term goal here? To one day perfectly print complex, fully functional human organs for transplant directly from a patient's own cellular data. Absolutely mind-blowing. And if we zoom all the way out to the macro scale, the future is just as wild. We now have giant robotic towers functioning as massive FDM extruders, squeezing out layers of concrete to 3D print entire buildings. Through contour crafting, they can trowel vertical walls layer by layer. And get this, because it costs so much to transport building materials on a rocket, we are actively planning to use this exact textbook technology to print permanent habitats on the Moon and Mars, using native lunar dust and Martian red soil as the raw material. We've gone from printing plastic toys on a desktop to the very real prospect of printing living tissue and homes on other planets. So knowing that we can now completely bypass traditional tooling, knowing that we can transform digital ideas into physical reality layer by layer with virtually any material, I leave you with this final exciting thought. What will you design? Thanks for joining me on this explainer, and keep learning.